So in the last lecture of electric and hybrid vehicles, we have seen some vehicle fundamentals, right? We have started with the dynamic equations, and then we have seen the tire ground adhesion and the maximum tractive effort of the vehicle, whether it is an electric vehicle or gasoline powered vehicle, right? So moving on with the electrical fundamentals, now today what we need to do is we need to see the characteristics, vehicle power plant characteristics. Okay, as we know, power plant, what do you mean by power plant? Whenever we are using electrical motor, then this will be our power plant, and in case of IC engine will be the power plant. Okay, so what are the characteristics of this power plant? That means if we are talking about the electrical motor, then what will be the characteristics of the power plant? And if I am talking about the IC engine, then what will be the characteristics of the power plant? Okay, so if we talk about the limiting factors to the maximum tractive effort, which we have discussed yesterday, okay, so there are two limiting factors, okay, that will limit the maximum tractive effort of a vehicle. The first one is the maximum tractive effort that the tire ground contact can support. Okay, first one is the maximum tractive effort that the tire ground contact can support. Okay, so the equation pertaining to this we already have derived yesterday. That was Ft max. The equation was Ft max is equal to mu mvg cos alpha into Lb plus Fr Hg minus Rd divided by L, and the entire term is to be divided by 1 plus mu Hg by L. Okay, so this was our equation which we have drawn. Similarly, when a vehicle is drawn with the rear wheel, at that time also there was the equation, and we also have derived that equation, right? So in that case, when our vehicle is driven with the rear wheel, at that time the maximum tractive effort is given by mu mvg cos alpha into La plus Fr Hg minus Rd divided by L upon 1 plus mu Hg by L. Okay, so this is our limiting factor to the maximum tractive effort, right? And second is the tractive effort that the power plant torque. Second one is the tractive effort that the power plant torque, sorry, power plant torque is there. Power plant torque with given driveline gear ratios. With given driveline gear ratios can provide. Okay, This was also seen by us in yesterday's lecture. We have derived the equation which was equal to Ft is equal to Tp Ig I0 eta T divided by Rd. Okay, so this was the equation. So these two are the limiting factors to the maximum tractive effort, right? So now whenever these two will be smaller, at that time it will determine the performance potential of the vehicle. Okay, so for on-road vehicles, the performance is usually limited by the second factor. Okay, and if you want to predict the overall performance of the vehicle, then we need to consider the power plant as well as the transmission characteristics of the vehicle. Okay, so this is the reason why we require to understand the vehicle power plant characteristics first. Okay, so talking about these power plant characteristics now, for vehicular applications, the ideal performance characteristic of a power plant is what will be the ideal performance characteristics? It should be constant power output over the full speed range. Okay, this is what we require. And what about the torque? The torque varies with speed some hyperbolically, right? So let us try to draw the ideal characteristics. We know the characteristics which is offered by electrical motor very well. Okay. Say on the x-axis we are taking speed as variable, right? And on the y-axis torque will be there and power will be there. Okay, now what is the ideal power plant, ideal motor, which will require the constant power throughout the different speed range? Okay, this is the ideal condition. Okay, so let me draw the ideal condition. We will start from 0. In no time we will reach over here somewhere, right? And then when speed increases, my power remains constant. Okay, so this is the ideal characteristics of power. Similarly, if I talk about the torque, then what will happen? Then you knew that initially when our vehicle is at standstill, at that time it will require more starting torque. Okay, so at standstill, at zero speed, our torque will be maximum like this, right? And then once power gets constant, what is going to happen? Torque requirement will start reducing in this particular fashion. Okay, so this is the ideal performance characteristic for a vehicle traction power plant. Ideal performance characteristics for a vehicle traction power plant. Okay, so this is the thing. Now here you can see, as at low speed the torque is constrained to be constant so as not to be over the maximum limited by the adhesion between the tire ground contact area, right? So this constant power characteristic will provide the vehicle with a high tractive effort at low speeds, where demands for acceleration, drawbar pull, or great climbing capabilities are somewhat high. Okay. Now talking about the IC engine, since the internal combustion engine and electric motor, these two are the most commonly used power plant for automotive vehicles to the date, right? So it is appropriate to review these basic features of the characteristics that are essential to predicating the vehicle performance and driveline design. Okay, say so representative characteristics of say gasoline engine in full throttle, and we will also consider the characteristics of electrical motor at full load. Okay, then we should compare these two with the ideal one. Okay, this is my ideal characteristics. This should be the characteristics of the power plant, whether it is an IC engine or it is an electrical motor, right? So talking about the gasoline powered vehicle, gasoline engine, whenever we talk about the characteristics of this, then okay, on x-axis I am considering the speed in RPM, right? And here we will be considering power in kilowatt. Okay, so this is 0, 20, 40, 60, 80 and 100, right? Similarly, speed is in RPM, so 1000 RPM, 2000 RPM, 3000, 4000 and 5000 RPM. Okay, so now we are talking about the power curve. Okay, actually this should be the ideal power curve, right? The one with the green line. And whenever we talk about the gasoline engine, now power curve will be somewhat like this. Okay, this will be the power curve in case of gasoline engine. And when we talk about the torque curve, then torque curve would be somewhat like this. Okay, so this represents torque and this green line represents the power. Okay, now we will talk this about later. First, let us draw the characteristics when my power plant is electrical motor. Okay, so this is my zero speed, 1000 RPM, 2000, 3000, 4000 and 5000 RPM. Again, motor power will be in kilowatt. Okay, so in this particular case, you will see that our characteristic is somewhat similar to the ideal one, like this. And when we talk about the torque, at that time we will get this kind of characteristics. Okay, so these are the characteristics of the gasoline engine and electrical motor, right? So now we talk about this IC engine. Okay, the internal combustion engine usually has torque speed characteristics which is far from the ideal performance characteristics required by the traction. Okay, it starts operating smoothly at ideal speed, right? Good combustion quality and maximum engine torque are reached at an intermediate engine speed, you can see, right? And as the speed further increases, what will happen? The mean effective pressure will decrease. And because why? Because of the growing losses in the air induction manifold and a decline in engine torque. So power output, however, increases to its maximum at a certain high speed. And beyond this point, what will happen? See, this is my maximum power over here, right? And beyond this point, the engine torque decreases now more rapidly with the increasing speed. Okay, so this results in the decline of engine power output. In vehicular applications, the maximum permissible speed of the engine is usually set just a little above the speed of the maximum power output. Okay, so the internal combustion engine has a relatively flat torque speed profile. You can see if you compare with the ideal one, then it is relatively flat, right? The one, this is hyperbolically, right? So consequently, what will happen? A multi-gear transmission is usually employed to modify this particular system. Okay, the torque speed characteristics, and that is why multi-gear transmission was taken. Okay, so now what will happen when we use the multi-gear transmission in this particular case, right? Let us try to understand the need of multi-gear transmission. Say our vehicle is in, this is my vehicle speed and this is the tractive effort on the wheel. Okay, tractive effort on the wheel, which is nothing but the torque in kilonewton. Okay, so if I talk about the first gear, then first gear will have such characteristics. Okay, then if I talk about the second gear, then second gear will have this type of torque speed characteristics. Then in third gear, we will have these characteristics, and finally in fourth gear, the characteristics would be like this. Okay, so ideally speaking, if we are talking about the average characteristics of all the four gears, then we will be getting these characteristics. Okay, so this one is for first gear. This is the characteristics for second gear. This will be for third gear, and this one is for the fourth gear. Right. So this was about the gasoline engine. Now compare these two things. Okay. Here you can see the torque speed characteristic is quite flat. But if you compare the average of these four gears, then we will get the characteristics which is almost similar to the ideal performance characteristics, which is the required one. Okay. So this is how the gear system comes into the picture for transmission. Right. Now, on the other hand, we are available with the electrical motors, right? And electrical motors usually have a speed torque characteristics which is much closer to the ideal one, as you can see, right? So generally, the electric motor will start from zero speed, okay? And as it increases to the base speed, okay, let us say this is my base speed. Okay, this is the base speed of the motor. Okay, so as it increases to the base speed, the voltage will increase to its rated value while the flux remains constant. Okay, this is what happens. You have already gone through the characteristics of induction motor very well, right? So this is what happens in the motor. Up to base speed, what will happen? The voltage up to base speed, the rated voltage will be achieved and our flux will remain constant. Now what happens when we go beyond the base speed? Okay, so beyond the base speed, the voltage still remains constant, but the flux will now get weakened. Okay, and this will result in constant output power while the torque will decline hyperbolically with the speed. Okay, so since this torque speed profile of an electric motor is close to the ideal one, a single gear or double gear transmission is usually employed. Okay, so in this particular case, whether it is a single gear or a double gear, we will have, so this is my torque in kilonewton, and here we will have speed in kilometer per hour. Okay, so it will be like this. Up to base speed, flux remains constant, and then above base speed, the torque will decrease hyperbolically like this. Okay, so this is the characteristic of electric motor torque speed characteristics, or you can say the performance characteristics. Okay, so this is our performance characteristic of gasoline engine, and this is my performance characteristics of electrical motor which are used for traction. Okay, Similarly, this circuit belongs to the tractive effort of internal combustion engine and a multi-gear transmission vehicle, right? And this is my tractive effort of a single gear electric vehicle, right? Versus the speed, of course, right? So these are the power plant characteristics of the gasoline engine as well as electrical motor. Now, similarly, if you want to predict the behavior of the system, then you also need to know the characteristic of the transmission. Okay, so the second thing you need to know is the transmission characteristics, right? And this transmission characteristics basically is of the mechanical side, automobile side, right? So the transmission requirements of a vehicle depend on the characteristics of the power plant, right? And the performance requirement of the vehicle. And we have already mentioned previously that a well-controlled electrical machine, such as the power plant of an electric vehicle, will not need a multi-gear transmission. But an internal combustion engine must have a multi-gear or continuously varying transmission to multiply its torque at low speeds, right? So the term transmission here includes all those systems which are employed for transmitting engine power to the drive wheels. Okay, so for automobile applications, there are usually two basic types of transmission. We know one is the manual gear transmission and another one is hydrodynamic transmission, right? We have two types of transmission. One is manual gear transmission and another one is hydrodynamic transmission. Okay, so talking about the manual gear transmission, now whenever we talk about this manual gear transmission, it consists of say clutch, gearbox, final drive and drive shaft. Okay, which we have already seen in the last lecture, right? So the final drive has a constant gear reduction ratio, or you can say differential gear ratio. And the common practice of requiring this direct drive in the gearbox to be in the highest gear determines this particular ratio. Okay, and this gearbox provides a number of gear reduction ratios which are ranging from 3 to 5 for passenger cars and even more for heavy commercial vehicles that are powered with either gasoline or diesel engines. Okay, so the maximum speed requirements of the vehicle will determine the gear ratio of the highest gear. Okay, on the other hand, the gear ratio of the lowest gear is determined by the requirement of the maximum tractive effort or the gradability, right? So the ratios between them should be spaced in such a way that they will provide the tractive effort speed characteristics which are close to the ideal one. Okay, and what is the characteristics of the ideal one? Let us see one more time over here. This is my tractive effort. Okay, so as we know that whenever we are having a first gear at that time, such characteristics will be there: second gear, third gear and fourth gear, right? So ideal tractive effort will be like this. This is my ideal tractive effort. Okay, so here in the first iteration, gear ratio between the highest and the lowest gear may be selected in such a way that the engine can operate in the same speed range for all the gears. Okay, and this approach will benefit the fuel economy and performance of the vehicle. Say for instance, in normal driving, the proper gear can be selected according to vehicle speed to operate the engine in its optimum speed range for fuel saving purposes, right? In fast acceleration, the engine can be operated in its speed range with high power output. Okay, so this is the approach which needs to be considered, right? And say, let me try to draw the demonstration of this vehicle speed range and engine speed range for each gear. Then you will understand it very well, right? So here on the horizontal axis, we will consider engine speed, right? On the vertical axis, let us say our different speeds are there. Say V1, then V2, V3, and V4. Okay, so these are the different speeds which are to be achieved like this. Okay, so what we are doing, whenever we are moving from 0 to V1, at that time, let us say our gear is the first gear. Okay, then from V1 to V2, we will use second gear. Then from V1 to V2 to V3, third, and V3 to V4, fourth gear needs to be used like this. Okay, right? So here you can see that from 0 to V1, I have these characteristics, right? Excuse me for a while. Okay, so this was my first, right? Then from 0 to V2, we have this 0 to V3 and 0 to V4.
Sir?
Hello.
Yes, sir. Sir, on
Uh,
vertical axis, we have taken which parameter?
Speed, vehicle speed,
And on horizontal?
engine speed,
Engine. Okay,
engine.
sir.
Okay. See, on vertical axis, we have considered vehicle speed. Okay, and this is my engine speed, which will definitely be different, right? And it is related to these gear ratios which we are going to use, right? So these are my typical characteristics. Now let us understand this 4-speed gearbox very well, right? So you can see, suppose this is my 1 speed range, then my engine is operating in this particular speed range. Okay, I will consider this where engine operating speed range. Okay, this is the thing. Now consider we have 4-speed gearbox. Okay, so we let us try to establish the relationship between these gearboxes, right? So let us say IG1 upon IG2 will be equal to IG2 upon IG3 will be equal to IG3 upon IG4, and that is equal to kg. Okay, so this kg will be Ig1 upon Ig4. Okay, so this Ig1, Ig2, Ig3 and Ig4, these are the gear ratios for the first, second, third and fourth gear respectively. Okay, so in a more general case, if the ratio of the highest gear, say IGN, in this particular case IGN will be there, right, and the ratio of the lowest gear, which is Ig1 in our case, right. So this have been determined and the number of gears is known, then you can find out the factor kg. Okay, so factor kg is given by Ig1, my lowest ratio, IGN, the highest gear, up 1 raised to Ng minus 1. Okay, so this is the equation which is used to find out the factor kg. And you can also find out the each gear ratio. Okay, say gear ratio Ign minus 1 is given by kg times Igm. Okay, then Ign minus 2 will be equal to k square g Ign and so on. Okay, so Ig2 will be equal to kg raised to Ns minus Ng minus 1 Ign. Okay, let us say equation number 2. Okay, so for passenger cars, to suit these changing traffic conditions, the step between the ratios of the upper two gear is often a little closer than it is based on this particular equation. Okay, so we can say this is the condition that Ig1 upon Ig2 should be greater than Ig2 upon Ig3 should be greater than Ig3 upon Ig4, right? So this in turn will affect the selection of the ratios of the lower gears, and for commercial vehicles the gear ratios in the gearbox are often arranged based on these particular conditions only. Equation number 3. Okay, so here we have some idea about the tractive efforts of a gasoline engine vehicle with the 4-gear transmission, right? And if it is an electric vehicle, then with single gear transmission, right? So this particular, let us try to draw one more time over here, and this particular figure will show, okay, for electrical vehicle this should be the characteristics, and let us say this is my first gear, here is my second gear, this is our third gear, and this one is fourth gear. Okay, so this is the characteristics pertaining to gasoline engine with 4-gear transmission. With 4-gear transmission, and the one with the green line was electric motor with single gear transmission. Okay, so this figure shows the tractive effort of a gasoline engine vehicle with 4-gear transmission and that of an electric vehicle with single gear transmission. And it is clear that the electric machines with favorable torque speed characteristics can satisfy tractive effort with simple single gear transmission, right? So this was about the manual gear transmission. Similarly, if we have hydrodynamic transmissions, then also we will have certain characteristics, performance characteristics of the device, right? So This is what we need to know. Now, the best part of this vehicle fundamentals is the performance of the electric vehicle, right? So whenever we talk about the vehicle performance, at that time we will talk about its maximum speed of a vehicle, its acceleration performance, then you can also say the operating fuel economy of the vehicle. Okay, so let us say maximum speed of a vehicle and acceleration performance as well as gradability of the vehicle in terms of vehicle performance, right? And this is what matters to us whenever we are designing a good electric vehicle. At that time, this parameter must be taken into consideration. Vehicle performance. Okay, so the performance of a vehicle is usually described by its maximum cruising speed. Okay, maximum cruising speed or a maximum speed, then gradability, and acceleration. Okay, so the prediction of vehicle performance is based on the relationship between tractive effort and vehicle speed, okay, which we already have discussed. For on-road vehicles, it is assumed that the maximum tractive effort is limited by the maximum torque of a power plant rather than the road adhesion capability. Okay, so the depicted tractive effort and resistance, we know three types of resistance: rolling resistance, aerodynamic drag, and grade resistance. Okay, FR, FW, and FG. On they are helpful for vehicle performance analysis in our particular case. Okay, for a gasoline power engine, which is a 4-gear manual transmission vehicle, and electric motor powered, which is single gear transmission vehicles. Okay, now let us see these characteristics: tractive effort in terms of some percentage, okay, or a resistance on a grade, such that we will get a clear cut idea. Okay, so this particular figure I have taken from the research paper of IEEE, right? So it shows a very good studies on gasoline powered engine as well as on electric motor engine. Okay, single speed transmission, right? So again, we will consider the speed on the vertical axis and tractive effort as well as resistances on the vertical axis. Okay, so here I will consider speed in kilometer per hour, and for electric motor also it is speed in kilometer per hour, and here we will use tractive effort. Okay, so characteristics is very well known to you. Okay, now this time we will use some ranges. Okay, 50, 100, 150, and say 200. Okay, now we have the characteristics, okay, very well known to us, right? So let me draw these lines first. Okay, these are the reference lines for us. like this, right? And if we consider the first gear, then we will have these characteristics. Okay, this is for the first gear. If we consider the second gear, then we will have this kind of characteristics. If we consider the third gear, then the characteristic would be like this. And for fourth gear, this would be the characteristics. Okay, so these are the different characteristics. Okay, so the one with the purple line shows us the tractive effort. Okay, this purple line shows us the tractive effort, and this black line shows us the resistance on grade. Right, then let me give you the values. Say this is my 0 degree or 0% value. Here it will be 5 degree, 8.7%, 10 degree, 17.6%, 15 degree, 26.8%, 20 degree, 36.4%, 25 degree, 46.6%, and 30 degree, 57.7%. Okay, so this will be for the case. And here, let us say this is my maximum speed. Okay, now similarly, when I talk about the electric motor, at that time we know the characteristics of electric motor, right? You will have a constant torque for some time, and then it will decrease hyperbolically like this. Okay, so this will show us the maximum speed when the torque is minimum. Okay, so for 0, 1, 2, 5, 6, and say 7. Now when we talk about the resistances, this will be the resistance like this. This shows the second value. This is my third. This third, sixth, and this one. Okay, so these are the different values. Say this represents the 0 angle. This is representing 5 degree angle. Percentage is 8.7. 10 degree, 17.6%. 15 degree, 26.8%. 20 degree, 36.4%, and finally 25 degree, 46.6%. Okay, so this particular figure shows the performance and a vehicle performance analysis. Okay, for a gasoline engine powered vehicle and electric powered vehicle. Now talking about the maximum speed of a vehicle, right? The maximum speed of a vehicle is defined as the constant cruising speed that the vehicle can develop with full power plant load on a flat road. Okay, so the maximum speed of a vehicle is determined by the equilibrium between the tractive effort of the vehicle and the resistance or the maximum speed of the power plant and the gear ratios of the transmission. Okay, so the tractive effort and resistance equilibrium can be represented as, we know both the equations very well, right? We already have derived TP Ig I0 eta t upon Rd, which was equal to mv g fr cos alpha plus half rho a Td AF V square. This is aerodynamic drag. The second term indicates aerodynamic drag, right? So this equation indicates that the vehicle reaches its maximum speed when the tractive effort represented by the left hand side term equals the resistance represented by the right hand side term. Okay, so the intersection of the tractive effort curve and the resistance curve represents the maximum speed of the vehicle, as you can see in this particular figure, right over here, this point and this point. Okay, whenever intersection is there, right? So this characteristic would be somewhat like this. There should be an interaction point. Okay, so this will be our maximum speed of the vehicle. Okay, so here it should be noted that for some vehicles no intersection exists between the effort curve and the resistance curve because of a large power plant or large gear ratio. In this case, the maximum speed of the vehicle can be determined by the maximum speed of the power plant, or the maximum speed of the vehicle can be written as Vmax is equal to pi np max Rd upon 30 I0 Ig minimum meter per second. Okay, so here np max and Ig min, these are the maximum speed of the engine and the minimum gear ratios of the transmission respectively. Okay, so this is what we have, the maximum speed of the vehicle. So if you have the knowledge of this torque speed characteristics of the IC engine or electrical motor, and you know the values of the resistances, then draw the resistance curve, draw the torque speed curve, and when it intersects each other, that will give you the value of the maximum speed for selected transmission. If it doesn't intersect with each other, then we have this equation. You can use this equation. Vmax is equal to pi np max Rd upon 30 I0 Ig minimum. Okay, where np max is the maximum speed of the engine and Ig minimum is the minimum gear ratio of the transmission. Okay, again I need to tell you, we need not to derive entire equations, right? It is the direct equations we are going to use from the automobile engineering, right? Now the next term after maximum speed is the gradability. Right, so gradability is usually defined as the grade or grade angle that the vehicle can overcome at a certain constant speed. Okay, it is nothing but it is a grade or grade angle that the vehicle can overcome at a certain speed. Okay, certain constant speed. Okay, so for instance, the grade at a speed of 100 km per hour. Okay, if we consider it. Okay, so for heavy commercial vehicles or off-road vehicles, the gradability is usually defined as the maximum grade or grade angle in the whole speed range. Okay, so when the vehicle drives on a road with relative small grade and constant speed, the tractive effort and resistance equilibrium now can be written as Tp I0 Ig eta t by Rd equal to mvgfr plus 1 by 2 rho a cd af v square plus mvgi. Okay, so what will happen to this I will be equal to Tp I0 Ig eta T by Rd minus Mv GFR minus 1 by 2 rho A CD AF V square by Mvg, okay, which is equal to say D minus Fr, okay, where D is equal to Ft minus Fw aerodynamic drag divided by Mv into G. Okay, so that is equal to Tp I0 Ig eta T by Rd minus 1 by 2 rho A CD AF V square by Mvg. Okay, so this is called the performance factor. This D is called performance factor. Okay, so while the vehicle drives on a road with a large grade, the gradability of the vehicle can be calculated as sin alpha equal to D minus Fr square root of 1 minus D square plus Fr square upon 1 plus Fr whole square. Okay, so the gradability of the vehicle can also be obtained from the diagram, okay, in the previous figure which we have seen, right, in which the tractive effort and resistance are plotted, right, over here. Okay, so from this diagram also we will be able to find out the gradability like this. Okay, 5 per 5 angle, then angle, 15 angle, 20, 25, 36, etc, etc. Okay, so this was the performance parameter, one of the performance parameter, that is gradability. Okay, so we have seen the maximum speed as well as gradability of the vehicles. Okay, so we shall stop here. In the next lecture we will see the acceleration performance of the vehicle, and then we will move on to the fuel economy of the vehicles. Okay, and then lastly we will see the braking performance of the vehicle, and then we will start with the basic electric vehicles, right. So if you have any questions, then you are free to ask.